We're going to dive right into Chapter 2, and Section 2.1 in your textbook begins with a discussion of average speed and instantaneous speed. So as you take these notes, I want you to think about connections that you notice between what we did in class today, where we found the slope of a curve whose slope kept changing, and what we learn here about average speed and instantaneous speed. So average speed, you probably already kind of have an idea in your mind what average speed is. You take however far you go and you divide by how long it took you. So if you drive 200 miles and it takes you 4 hours, your average speed, the number part we can calculate with 200, the distance, divided by the time, 4. What we want to also make sure that we watch out for in our calculus study is to notice the units. So the speed is going to be the distance divided by the time, and the units on distance are miles per hour, or miles, and the units on time are hours. So your result is going to have units of miles per hour. So 200 miles divided by 4 hours makes 50 miles per hour. There's a place in your book to write, your paper to write in that note. So something that will help you remember that this is the computation you have to perform to find average speed. Distance divided by time. Distance traveled divided by time. Now watch this. If I write that expression, if I write that computation using this notation, all of a sudden, also delta x, x standing for distance, and the delta meaning change in distance. So where you ended up minus where you started, and delta t meaning the change in time, so how much time went on during the driving that we're talking about. So in this case, a time change of 4 hours from when you started to when you stopped. When I write it with that delta notation, it hopefully calls to mind this idea that we've been using already, that we're going to be studying the slope. So if I think about, let me look at this. Think about graphing distance traveled as a function of time. If I happen to drive at exactly 50 miles an hour for my whole trip, then when I make that graph of distance versus time, I'm looking here, I'll have a linear graph. And in fact, the slope of that graph is going to be 50 miles per hour, which happens to be the same as the average speed. So that's why that computation looks the same as the calculation for slope. Just notice that in calculus, we have to acknowledge that you don't always drive exactly 50 miles an hour, but we can still take distance traveled divided by the time that has elapsed, and that computation will still give us the average speed. So on this graph, I might use that ordered pair and that ordered pair, and if I performed a computation to get 50 miles per hour as my average speed, that would be the slope of that line. But if I had that same point and that same point on this other graph, even though I haven't been driving at a constant speed, I'll still have the same average speed because I'll still have traveled 200 miles in 4 hours. So distance divided by time gives average speed, even if you haven't been driving exactly the same speed the whole time. Contrast with this idea that of instantaneous speed. If at some time during that trip, I look down at my speedometer, I might be going 65 miles an hour, or I might be going 20 miles an hour, or maybe I pulled over to the side of the road and I'm going 0 miles an hour. Whatever that speedometer says at that exact moment in time is my instantaneous speed. It would be the speed that the police officer read on their radar gun if they radar gunned you while you were driving. So speed at one exact moment in time might be different than your average speed for the whole trip. I want to understand that difference between average speed over a whole trip and instantaneous speed. All right, there's a place to write this example in your notes. Let's talk about computing average speed. Probably straightforward. If I have a rock that's going to fall from a cliff and I want to find its average speed over the first 2 seconds that it's falling, I'm going to need to compute the change in its position, which is called distance, the distance that it falls, and the change in the time. So this is from 0 seconds to 2 seconds. That changes 2 seconds. And I'm going to do that division problem. So distance traveled divided by time falling. So if I wanted to know, whoops, that's supposed to be the pen. I wanted to know time and distance at time 0. I could replace the time in this function was 0, and 16 times 0 squared, that's 0. So after 0 seconds, it's fallen no distance. That's what that means. And now I want to know the distance that I've traveled at the end of 2 seconds. So I'm going to evaluate my distance function at time 2. That's going to be 16 times 2 squared. Make sure you do this squaring first. So 16 times 4, 64. So now when I do the computation, that's change in distance, so 64 minus 0, feet traveled in 2 seconds, gives me an average speed of 32 feet per second. Now, the calculus question, how fast is the rock going at exactly 2 seconds? So I might like to use that same setup, that same calculation, change in distance divided by change in time. But now I have a big problem. My change in time, I don't care about the speed of the rock in between 0 and 2 seconds, or in between 2 seconds and 3 seconds. I care about the speed of the rock in an instantaneous moment at the time interval from 2 seconds, the time interval from 2 seconds to 2 seconds. So that's a change in time. There's no change. The 2 is the only time I care about. I don't have a second time to use as my second time value, so I can do a subtraction in my denominator, change in distance over change in time. That means I'm going to have a 0 in my denominator, and that leads to the first big problem, which actually led to the whole invention of calculus. How can I compute this idea of slope, change in distance over change in time, if my change in time, my denominator is going to be 0, and division by 0 is undefined? So before I move on to the next slide, let's just recall what we did here to compute average speed. We figured out, I'm going to call that speed, was the change in distance divided by the change in time. Well, how did I find the change in distance? I had to figure out f of 2 and subtract f of 0 over the change in time. The beginning time was time 0, the ending time was time 2, so my change in time was 2 minus 0. So that gave me average speed over the time interval 0 to 2. So if I think that the same calculation might work, except for the 0 over 0, the 0 problem in my denominator, let's explore what I could do. Instead of finding the average speed over time 0 to 2, if I care about the speed at exactly time 2, I might use the time interval from time 2 to 2.1, or maybe time interval 2 to 2.001, or time 2 to time 2.000000001. Then I won't have a 0 in my denominator anymore. And we could do that. In fact, we're going to talk about that as an option. But if I'm not really sure, how small do I have to make that change for me to get like pretty good answer, but not break my calculator trying to do that complicated math? So I'm going to use a variable, h. I'm not sure how much to make that tiny change, so I'm just going to give it a name, and that way I can change it around and try some different things out. So I'm going to have the 2 times I'm going to use, or I'm going to start at time 2, and my second time is going to be 2 plus a little bit, like probably a really, really little bit, but I'm not sure how small I have to make it. So I'm just going to give it a variable name. So that's what I have here. I'm going to do that same computation, change in distance divided by change in time, except instead of time 0 and 2, I'm going to use time 2 and 2 plus a little. So that's my first input is 2, my second input is 2 plus h. And in my denominator, I have the change in the time. So that's the second time, 2 plus h minus 2. Notice the 2's cancel, which is why I've simplified to h here. So now I have to, in this problem, I happen to know a formula for distance traveled. So instead of using f, I'm going to actually replace it with the actual function. And that was 16 times the input squared. In this case, I have 2 inputs, the input 2 and the input 2 plus h. So we could compute this. Notice there's only one variable in this expression. That's the variable h. I could try using some different values of h to see what my instantaneous velocity turns out to be. It'll only be an estimate because I can't actually let h equal 0. I'll have a divide by 0 problem. But especially if you had a computer or a calculator, you wouldn't mind doing this computation a bunch of times. So we're going to do that. I'm going to let h be 1, and then I'll let it be 0.1, then I'll let it be 0.01. I'm going to use some smaller and smaller values, see if we can get an idea for what's going to happen. And here's the result. I let h be 1, and then 0.1, and then 0.01, and you can see what happens to my instantaneous velocity approximation. I have a first approximation of 80 and then 65. It gets closer and closer and closer to 64. So I might predict that if I could think of a computation to do that didn't have a divide by zero problem, I might decide that the answer is probably going to be 64. So that's one way to investigate what's going on, is to try smaller and smaller values of h and actually compute them. But we're not going to always have a computer or a calculator handy, so I want to talk about another way that we could check this value. We can actually use algebra to simplify this expression. And to clarify, this is the part starting here, this algebra way to simplify this expression. That's what I want to go in your notes. That's what I'm expecting when you see the textbook problems. And this is what we're going to need to know to set the stage for our study in the rest of section 2.1. So we're going to use h to stand for a number really close to 0. We're not sure how close to 0. That's why we're still going to have it be a variable. We know we can't use 0 for h, because then we'd have this 0 in the denominator problem. But we wish we could use 0. So notice this expression. My function for the distance traveled is 16 times the quantity t squared. So I'm going to have two separate t values. I need to evaluate that. That's 2 plus h and 2. So I'm going to do what we practiced in class. Remember practicing this in the class? The next thing, if I want to try to simplify this, I'm going to expand that square of the binomial. So 2 plus h needs to get squared. That takes 4 multiplications. 4 plus 4h plus h squared is what we have here. That's the expanded version of that 2 plus h squared. So I can simplify that. 16 can get distributed. Notice 16 times 4 makes 64, but then I'm going to subtract 64. So what I end up with is 16 times 4h, that's 64h, plus 16h squared, all divided by h. Notice here, we can factor. So the common factor in that numerator is h. So I'm going to factor that, 16h. Oh, okay, h. So watch this, 64 plus 16h. That's going to get divided by h. Those h's can cancel, and I know this can simplify to 64 plus 16h. It's a 16h. So the thing to think about now is, what did I want h to be? I wanted h to be some number that's so small. I wanted to get smaller and smaller and smaller. I wished I could have made it 0, but I had that problem before. Notice that problem of dividing by 0 I don't have anymore. I've used algebra to make that divide by 0 problem go away. So now I can think about, if h is a number that's so close to 0, it's essentially 0. What is 16 times 0? 0. So I'm going to get that same result that I seem to get when I use a table, which is the instantaneous velocity is 64 feet per second. So there's a couple problems in your textbook for you to do. Notice the big difference between this example we just did and the instantaneous speed examples in your textbook. They might ask you to use a different input value. So every place that I use 2, you might have to use a different number. And they might give you a different distance formula. So where I was using 16t squared, you might have a different one. Maybe it's 5t squared, maybe it's 9.8t squared. So those are the two things that you might have to think about changing when you use this example to help you with the homework.